Hey, so welcome back. This is lecture 9. It'll be the second lecture we deal with when we're dealing with lists. The first lecture you saw, we talked about the list ADT somewhat, and also spoke about the array implementation of the ADT. This lecture is going to involve discussing extensively the linked version of this. So we're going to talk about what linked memory is and how we would use that linked memory to implement the list ADT. What we will talk about in the next lecture is then a little more extensive information on linking, and we'll conclude this all by talking about iterators, which will have application beyond just lists themselves, as you'll see in the section 4. So, first we want to discuss the idea of linked memory. Linked memory is extremely common in a number of data structures. And of course, this will be the simplest version we see here, but throughout the semester, we'll see many applications of linked memory. And all linked memory refers to, you may have well seen this in a prior programming class, it refers to the idea of various data structures holding pointers to other similar data structures of a similar type. And often those are smaller structures that compose a larger whole. Here what we're going to have is the idea of a node. This would be the data structure we're concerned with. Drawing it out, we have here the idea of an element, and I guess we can write out here the whole word element because I believe that is how it appears in our code. And then we have here what is often called next, which is a pointer to another node. So if we're going to draw or define this class out, I'm going to leave off for the moment things like constructors and the template line and that, just getting at the essential details of the member data. What this looks like is we have here a class node, and we have whatever the E-type would be inside a template, that is what the element is. So it's a holds integer or float or chord or whatever our E-type happens to be. And then the second member data is a node pointer itself. So even though the class is node, there's nothing that keeps us from having a pointer to a node. And that's what we have here, is that the class, one of the variables, will point to other objects of this type. And so we have that in that case. And so then what happens is that this a list is built from this concept. And so keeping that node in mind, we then chain together a number of these. And so we would have then here, say the element 2, pointing to 6, pointing to 8, pointing to 7, pointing to 1. Drop that down a bit. And that is then, we'll deal with that example extensively in this lecture today, but that would be an example of a linked list. This is known as then a linked list. By the end of this lecture, we'll see that often when we refer to the list ADT, we are generally referring to a linked list implementation of it. Not always, but often, since the linked list ADT, or the linked list implementation of the list ADT, tends to be a better choice in almost all circumstances. And so this is linked memory, but we can formally talk about the list ADT being implemented using contiguous memory or linked memory. The term linked list generally refers to a list ADT implemented with linked memory, and this is a far more common term than speaking of linked memory by itself. We talk about linked lists, and that's because the list ADT is almost always implemented using linked memory. Now, if you come from specifically our CS225, but more generally, if you come from a Java or even a C++ background, if you've seen some of C++, but in a lower level programming course that tended to emphasize recursion very heavily, as we do here, you may have seen a different form of linked list, and that form of linked list would have been a form of linked list in which this actually was the list. This was your list itself. You would have a value 2, and then some sort of next or tail, which would point to the rest of the list. But the idea would be the list class would be this node. And so if I had a L1 was a pointer to a list, it would point to this node, and then this would be a list pointer to another list, which would be a node, which would hold a value and a list pointer to another list. And so conceptually, this was the list itself. And what that would mean would be that an empty list meant L1 was equivalent to null. And that's one way of dealing with linked lists, a sort of recursive idea where we say our reference or our pointer is null if there are no elements. If there is one element, then our reference does indeed point to something, but its tail or its next field would be null, and so on and so forth. Where we actually basically view this rest of the list, our list is always viewed as a value and then another list. So it's sort of a recursive definition. In contrast, the way we're going to view this for this lecture and for our class here is going to be a little bit more complex. Instead of stating that the list itself is simply a value and the remainder of the list, which I guess abstractly could be thought of as you have your list, which is simply 2 and then some other portion of the list like that. So we'd say you have the value 2 and then another list. So it's a recursive definition. What we will be viewing it as is our list itself is a collection of nodes. The list is not the first node that points to another list. Rather, the list is a collection of nodes. So each of these is a node. You can think about putting them all inside a box. And this would be the list, L1. And L1's data members would not be value and next or value and tail. Instead, L1's data members would be simply a head pointer to the list, first node in the list, and then whatever other pointers you might have, and I'll draw them on the next slide. But L1, we typically, of course, have a current pointer and perhaps a pointer to the last node, a tail pointer, and then a size field. And those would be the elements of L1, not my first value and my first pointer to the rest of the list, but instead L1's values would simply have nothing to do at all with the nodes, and they would be head and current and tail and size. And then individually, we would allocate these nodes within the list. And one of the advantages to that approach is that if I want an empty list, here I'll draw this more extensively on the next slide, but here if we just have a head pointer and nothing else, then head being null is the null list. However, the list actually exists. And that's one of the advantages of sort of boxing up nodes nested within a larger list class rather than making the node itself the list object. One of the advantages would be that where in this case your empty list meant your reference was null, in this case you always have a list. Because if L1 is null, then if I want to say L1.insert, I can't do that. I have to first say L1 equals a new list, and so my procedure by which I might insert additional elements is different than the procedure by which I would allocate my first element. And so that's this recursive idea here. We end up with saying that I can't do that insert operation to insert the first node because calling insert off a null reference would be null. I would need to first create the new list. That would give me my first node with the tail being null, and then I could call insert or whatever after that. Where here, I have a L1 points to something right off the bat. It's an empty list, which means the internal variables are set to record no external nodes, but the list itself actually exists. So when it comes time to insert the first node, I can say L1.insert without any problem. Of course, I have to pass in a value in both those situations. But whatever that value happens to be, the idea would be I can always call insert on my list. I can always call remove on my list if there are nodes there. But the empty list is still a list, and I can still call insert on it, as opposed to saying, oh, the empty list is a null pointer. That means then that creating the first node is different than inserting subsequent ones. And while there are certainly advantages to the recursive approach as well, one of the big advantages of doing this different kind of approach, where you have the nodes are separate from the list as a concept, is that the list as a concept, when we create a new list, the list exists. Even if there are no nodes yet, the list itself exists. And so I can call insert on the list to insert the first node just as easily as I can call insert on the list to insert any other node. And so there's some appeal of consistency there. So that's how we're going to view the list. So I'm going to put this in more in detail on the next slide now. Our list class, now we'll have extensions to this and variations on it, as you'll see in section 4. For now, I'm going to do the simplest possible kind of thing, which is simply a singly linked list, and I'll sort of leave some complexity details off Things will get more complex though. I'm just letting you know right now I'm trying to keep things simple to illustrate the basic pointer manipulation operations. By no means are restricted to just what I have here. But your class, your list class here, would involve, well, firstly, you'd have your class node that we had on the previous slide. So this would be nested, the definition of node would be nested inside the list class, meaning now the node is not accessible to sort of a global community. It exists only within the context of the list class, which is nice because then your users don't know about the node implementation. And you'll see more syntax like that in the fourth section. Then once you have that existing, you can say I have a node pointer called head. We, of course, discussed last time the need to have some sort of current reference marker, so I can have a node pointer called current as well. Often, what we will often have for efficiency is a third pointer called tail. So tail would point to always the last node, where head would always point to the first node, and current points to whatever our currently selected node is. And then we likely would have a size field as well, just as we did with the array version last time. And we, of course, would have interface functions as well, but this would be the data members. We'll have 4 data members when we create a list, and therefore, our list can be thought of as a situation like this, where I have a head pointer, and the empty list would make it null. The empty list would have a tail equal to null, would have a current equal to null, and then perhaps your size field is here, and that's equal to 0. And then when I insert my first, so this is your L1, and whether L1 is the name of the list or whether it's a pointer to the list, the idea would be here, this is our list object. And then when I insert my first element, then of course that first element would be simultaneously the head and the current and the tail of the list, and your size would be 1. And then you can, of course, change head and current and tail as you add more elements. But the idea is that head, current, tail, and size are our data members. That's their initialization when we have no elements. When we insert our first element, then they all point to that node. When I insert the second element, then head and tail would point to 2 different nodes, and current would point to one of those 2 nodes, and so on. But that's the idea behind our list class. And so it's important to recognize the difference between saying I have a list object within which I allocate nodes, and the recursive definition, which would say my list is the node, and then it points to another list. Here our node points to other nodes, and the whole thing is wrapped in one giant list that provides the interface. So therefore, you always have a list even when your list is empty. An empty list is still a legitimate list, rather than saying the empty list is some non-existent concept. So that said, what we then need to do is consider how the various operations would run. So let's go ahead and put back up that conceptual list and a 5-node example. And what we have here, this is, again, the conceptual list. So we have 2, 6, 8, 7, 1, and 8 will be current. So when we've got that established, what we have then is, here's head. We point to 2, which points to 6, which points to 8, which points to 7, which points to 1. And then this whole thing is wrapped up. Eventually I'm going to stop drawing this box around it, but for now I want to make the box clear. So here we have a tail pointer. Our size is 5, and current points to 8. And so that's our list. Whatever the name of the variable of the list is, this is the list object that has these various nodes. And so let's say L1 is a pointer to this list. Then when I call functions such as L1 arrow, say insert after, which we will talk about later on, not at the moment, I'm inserting after, well, we're doing integers here. So let's say I'm going to insert 0 after current. What that would do then is insert 0 after 8. And so that's the idea of my list and how I would call things on it. Of course, if L1 was just the variable name of the object rather than a pointer to it, then I would say L1 dot insert after. But essentially, we deal with the same concepts here. So that would be how the conceptual list would be translated to the overall list, or the implementation. And we saw the same thing with an array. how the conceptual list was translated to an array implementation, where we had a five elements legitimate, and current, the index held 3, because that would be the index of 8. Here, current points to the node containing 8. So unlike with the list, or unlike with the array implementation, current is now a pointer, not an integer that holds an index. But effectively, the same idea is implemented. We have current somehow refer to which of the elements is the current element. So let's consider now a few functions, just so we get a feel for exactly how we would make use of this. And the first one we'll consider will be the same one we considered first before, namely, let's deal with forward 1. And again, I'm just worrying about rough pseudocode here, so I'm not going to worry about scoping it to the list class or return types or anything like that. I'm just, forward 1 is the function we want to run. And so the question is, how would this work? And again, special cases I'm leaving out too, so we're not going to worry about what it means to run forward 1 at the end of the list. Just in general, the key idea behind this, and then all the trimmings you could add yourself or see in section. So if we're going to deal with forward 1, what we want to do here is, of course, move the current marker from 8 to 7. That means ultimately this pointer has to stop pointing to 8 and should point to 7 instead, or that it should stop pointing to the node containing 8 and should point to the node containing 7 instead. And if we want current to point to the node containing 7, it has to have the address of the node containing 7. And there's only one place in our entire system where that address is stored. And that place is inside the next field of the node containing 8. Because that address then is, since it's pointing to 7, that means that this field holds the address of that node. So we need to read that next field in order to move current to 7. Ultimately, what I want to do is change the value of current. So I'm saying current equals, because I'm going to write a new value into it. And what it will equal will be the address stored right here. Or in other words, the value of this pointer. And that's going to be accessible by saying we'll dereference current to get this node, and then access the field sitting there. So I could have said current equals dereference current dot next. Dereference current to get this node, and then from that node select the next field, and that would give me that pointer, and I can move then current to where that pointer points to. So now this holds the address of the node containing 7, and so does current. And of course, we've seen that that's not the ideal way to write this out. C++ provides the very nice arrow syntax for a combination dereference member access. So this would be the better way to do this. Current equals current arrow next. Those two lines mean the exact same thing, but the arrow syntax is nicer to deal with because it's all in one place, and you don't need parentheses. So that would be the code for forward 1. If I want to move current forward 1 node, I simply am going to say current equals current arrow next. And that simple operation, moving a pointer to a node to the next node, is going to come into play in a number of places. When we start talking about iterators, it'll come into play in a few other places as well. But the basic idea of just saying current equals current arrow next, that's a very common thing in C++. It's basically the I++ of pointer operations when we deal with nodes and such. So that basic operation is very important to us. So that's forward 1. Now we can also talk about now what happens when we deal with information retrieval. And so we can now consider retrieve, which would return an E-type. And again, the use of this would assume the list actually does have elements and that current is not null, but we're not going to worry about those error checkings right now. So here we want the value that current points to, which is going to be 7 in this case. And we can do the same thing we did in the last example. When I wanted the next field of what current pointed to, I used current arrow next to get to it, which was dereferencing current and then accessing the next. And now I want to access the element instead of the next. So I would dereference current and then access the element from there. And the dereference and access together are the arrow operator. So what I can do here is say return from current, dereference, and then access from that cell the field element. And so that's what that line does. We're saying dereference current to get the node that it points to, which is the node containing 7, and then in that node access the field called element, which is the actual data value that holds 7 here. So, and then the dereference and access together are represented by the arrow operator, dash greater than. So there is retrieve, and so again we have this idea of current arrow whatever gives us the relevant value from the node. And if we run retrieve on the list we see in the picture, that would return 7. So hopefully it's clear that both of those are constant time. All we're doing here is retrieving, doing one dereference and retrieving a field, and the same thing back in forward one. All we were doing with forward one was saying retrieve a field from the node current points to, and then write that address into current again. And writing an address is a constant time operation, and dereferencing is a constant time operation. So there's nothing going on there that's of any complexity. Nothing for either retrieve or forward one depends on the size of the list. However, back one would be a different matter. And this is where things get interesting. I'm going to move this up now so you only see the list, not the conceptual version of it. If I want to move back one, what I essentially want to do is move current back to 8. It points to 7 now. I want to move it back to pointing to the node containing 8. But there's a difficulty in doing that. And that difficulty is, in order to do that, I need to store inside current the address of the node containing 8. When I wanted to move current from here to here, I was saying, find the address of the node containing 7 and write that in current. And I could get that address from this spot. What I need now is to take this address and write it back inside current. And the only place I know that address is inside the next field of the node before it. And the only place I would know that how to get to that next field would be to have a pointer to this node so I could access its next field. And the only way I know the address of this node is the pointer field of the next before it. And so on and so forth. That is, the way the linked list is set up, the way we have linked memory set up, each node always holds the address of the node after it, and that's the only place that address is stored. So if I want to know the address of the node containing 8, I'm going to need to know the address of the node containing 6 so I can get to this pointer. But if I want to know the address of the node containing 6, I'm going to need to know the address of the node containing 2 so I can get to that pointer. And if I had a bunch more elements before this, it would be the same thing for each one of them until finally I hit head. And I say, oh, I do know the address of the first node because head holds it. Head points to that node, so the variable head holds the address of the first node. And then from the address of the first node, I can then get the address of the second node by reading the next field of the first node. And then from the second node, I can then read its next field to get the address of the third node, and read its next field to get the address of the fourth node, and so on and so forth until we finally land at the node we want. That is, moving back one requires we start at the beginning of the list and traverse forward until we reach the node before current. Because that's the only way we'll be able to know the address of the node before current is to traverse forward to find it. We have to go through that path because we don't have the address stored any other way. So if you're going to deal with back one, as far as writing code, first thing you'd have to do is have a node pointer temp equals head. So we would position temp right there. Then what we would do is say, as long as temp's next field, the address held by temp next, is not equal to current. This is the short form. I mean, if current was your first node, you'd have to deal with that as a special case or rearrange this logic a bit. So again, I'm simplifying things to just the most common case to get at the rough idea. So there's certain, of course, other special cases you would need to worry about. But we can say here, as long as temp next, in other words, as long as the value this pointer points to is not equal to the node current points to, then I can say, use my iteration, or my traversal forward, and say temp equals temp arrow next. So I'll say, is temp next equal to current? No. Then move temp to here. Now, is temp next equal to current? No. Temp next points to the node containing 8. Current points to the node containing 7. So again, run temp equals temp arrow next and change temp to point to the node containing 8. Now is temp next equal to current? Yes. Here's temp. The next field is here, and that's the same place the current points to. So now I can leave the loop knowing now that temp points to the node before current. Because by definition, if temp arrow next equals current, then temp is pointing to the node before current. And then with that done, I can simply say current equals temp. And that will say, well, now move current away from 7 and point it back to the same place that temp points to, which was its original value of 8. And that effectively then moves a current marker from 7 back to 8 on the conceptual list as well. So that's back one. I can move this up a bit. That's back one. And the downside to back one here is it's going to be worst case linear time. The reason being that at the very worst, we might be trying to move back one from the very last node, which would mean this loop that traverses through the list until we find current would go through almost all the nodes, stopping finally at the node before last. Because if we're at the last node, then the one behind it is the one before last. So that would be basically going through the entire list. So in the worst case, we'll have to basically start at the beginning and traverse through almost the entire list, and that'll be linear time. As the list grows, the time for that operation would grow. And even on the average case, the same thing would apply. On the average, we would maybe look through half the list before we were able to find current. On the average, current would be positioned maybe halfway through. But that still means that we need to search half the list to find the node before current. It just means we don't need to search the whole thing, but you still need to look over half of it. And just like the analysis of the array methods that we did, or the array functions, traversing over half a linear list is still going to be linear time. It's just going to be half of what the worst case was. So there's this disadvantage here in that then back one runs in linear time. So with that said, we will now have this back one issue sort of come up a little bit in two of the next three functions we're going to deal with, and we'll see that often we can work around that. For the straight back one, there's no way to do it. But when we start manipulating nodes around back one, often we will be able to, in fact, deal with that issue. So we will come back to that. For the moment, let's put this list example back, and I'm going to stop drawing the box around it now. I'll just focus on this idea, the idea of the actual data members themselves. So here's 2, 6, 8, 7, 1. Here's current, and I'm just going to worry about those for the moment. I'm not going to worry about size and tail. They're there, assume they're there, but let's just focus on head and current. Those are the interesting ones to worry about. And what we're going to code at this moment is insert after, which takes in an E-type X, and then insert after the current position, which means conceptually for our list here, let's say we're going to run insert after 9. If I have here 2, 6, 8, 7, and 1, and I want to insert 9 after the current position, what I want to do is put 9 between 8 and 7. That's my goal here. So one thing we might notice is that in terms of the final state of this, we might point out that the final state is simply, and I'm going to now, your slide will just change. I'm going to actually put in a slate piece of paper here to indicate what happens at the end, and then I'll go back to the beginning picture. So what we have here is, what you'd like to see is we have the node containing, say, 9. That's what we're going to insert. This would point to 7. And then this pointer would point down here to 9. Ultimately, that's what we want our picture to look like when we're done, our implementation diagram, is that we would have 8 pointing to 9, pointing to 7, pointing to 1, and that's really what we have here. Down here we have 8 pointing to 9, pointing to 7, and then I've covered up 1 with a piece of paper, but that's what that would look like. Now the question is, how do we get from point A to point B? How do we get to this point given that starting situation? And that's where it gets interesting, and that's how we're going to take a look at this. First and foremost, above anything else, I will propose at this point the question to the class, what's the first thing we absolutely would have to do? And the answer would be, well, we're going to need to have, or what's one thing we definitely have to do, I should say, beyond the shadow of a doubt. And one of those things will be, we'll need to allocate a dynamic node. However else we get things to work, we will need to allocate a dynamic node to hold our value. So we may as well do that first. Let's say we have here a node pointer temp. Now what we could do is say temp equals new node, and then later on say temp element equals x. Because our parameter, which is 9 in our example, the more general parameter is just x. Now we can do that. We can declare a new node and then write x into its element pointer. However, we tend not to write things specifically out that way. The reason being that often we'll provide a couple utility constructors for the node class as well. And in that situation, when we're dealing with sort of this utility class, typically the node constructor will take the element as a parameter. So I would say here this. In place of those 2 lines above, I would have one line that says declare the temp variable and then set it equal to a new node. And of course, I could have just said new node temp semicolon and then temp equals new node as well. You can put initializations and declarations on the same line or not. Here we are. We're declaring and initializing on the same line. And in the process of that initializing a pointer value for temp to hold, we create a new node. So in terms of pictures, this looks like that. This constructor would also often set the pointer to null. So typically when you see a constructor, it would say read an x and set element to x, and then the pointer should be null. What you now need to do is write temp next should point to 7, as we saw in that previous slide, and 8's pointer should point to 9. And it's important the order you do these in, because if you simply say, well, now point 8 to 9, you lose this entire section of the list here, 7 and 1. You can't change this pointer. That's the only pointer that holds the address of 7. Until we've got the address of the node containing 7 tucked away somewhere, we cannot change this pointer. And that means that this assignment, where I write the address of the node containing 7 into this next field, that has to be done first. So I will say temp arrow next equals current arrow next. I'm saying the next field of the temp pointer is going to have stored inside it the address stored in the next field of the current pointer. So that's what temp next equals current next means. It means that we're taking the next value of the temp node and storing inside it the next value of the current node. And since the next value of the current node points to the node containing 7, the next value of the temp node will now point to the node containing 7. Once that's done, we have safely stored the address containing 7. Now we can change the next field of 8. And so now this can change to point down to here, and the code for that would be then, now that we've read current.next, we can write current.next, because there's no need to read it anymore. Current next equals temp. And those are the essential details, because you'll see now, if you do a traversal in the beginning, you'll say 2, 6, 8, 9, 7, 1. You've managed to traverse the list without a problem. And typically then what we would also do, not all the time, but sometimes you'll also see something like this, current equals temp, where current moves to point to whatever list element was just inserted. So current always would point to the most recent insertion. That's not ironclad, it's just used in many list classes, but I thought I'd throw that in there to let you know exactly what's going on. And you'd of course have to have in here a size function to increment the size, and you need to have a few other helpful list functions as well. But for the most part, that's all we need to do in insert after. Know where you're inserting after, know that current pointer, and then run this algorithm. So that's the insert after procedure. Now it's a little more interesting if we try and tackle the insert before procedure. Because at first glance, if we draw this pointer, or if we draw this list again, two, 6, 8, 7, and 1. And now we're going to run insert before. Again, this will be current. And here's our conceptual list. 2, 6, 8, 7, 1. And what we want to do is, since 8 is current, we're inserting 9 before 8. And so the sequence should be 2, 6, 9, 8, 7, 1, not 2, 6, 8, whatever. The 9 comes before the 8. So as a result then, what we are able to do here is, well, it looks at first glance like we need to change this pointer. I'm saying, well, if I'm going to insert before 8, 6 should no longer point to 8. The node containing 6 should point to the new node I'm going to allocate. And then we have that whole big argument again we had with back 1, where I said, well, if I want to change 6's pointer, I need to know the address of 6, and that means knowing the address of 2, so I can change 2's next, or read 2's next field, and so on. And so again, if we want to change the pointer behind us, the argument would be that we need to start at the beginning and traverse forwards until we reach 6, which is just before 8. Then we can read 6's next pointer. However, anything involving that back 1 loop is going to be linear time. And in the previous slide, if you inspect insert after very closely, you'll notice that code is constant time. All we have is a few declarations and pointer assignments and pointer accesses and such. Nothing that we've written there at all depends on the size of the list. I can have 20 elements or 200. This code doesn't depend on that at all. And what that means is that insert after will be constant time. We'd like insert before to be constant time as well, but it doesn't look at first glance like we can have it set up that way, because what we've got it set up here is that I need to change the pointer before 8. And that would require doing this back 1 type traversal where we start at the beginning, traverse up to 6, which is before 8, and then mess with things. So it seems like all hope is lost here as far as making it work in constant time. But it's not. And the key to realizing how to do this in constant time is to recognize a very, very important fact. Implementation does not matter to the abstract view. I'll say that again. Implementation does not matter to the abstract view, or does not matter in the abstract view. That was one of the points of encapsulation, one of the whole points of abstract data types. We could think about the item conceptually without worrying about its implementation. And that's important here because all I care about is that 9 ends up between 6 and 8. If I'm inserting before, I want this list with 9 inserted before 8 and thus inserted between 6 and 8. Nothing else matters. We, of course, would like a fast implementation of this. But in terms of correctness, that's all that matters. And I'm going to just pause in my speech for a minute and say, if I tell you that, can you now see how we can make insert before work in constant time? And if you want to think about it for a minute, then pause the tape. So I'll continue now. As far as making insert before work in constant time, the secret is to recognize that inserting the value into the abstract concept, the abstract list, and inserting it as a literal node in the implementation are two entirely different things. That might correspond. Last time I was inserting 9 after 8. The node I inserted also was inserted after 8. But they don't have to correspond, and in fact they won't here. What we're going to do is start out doing the exact same things we did last time. Namely, I will insert after 8. I'll allocate a node pointer and have it point to a new node containing whatever x is. So I've got that here. This is temp. I will then point temp next to this node. I will then point current next to the temp node. So now 8 points to 9 points to 7, just as we did in the previous slide. So up to this point, all I'm doing is rewriting code we just wrote on the previous slide. But now that that's done, now that the new node has been integrated into the list, what we will do is swap 8 and 9. So I can say E-type temp equals current element, and then current element equals temp element. Whoops, I didn't want this to be temp. Make this temp 2. So then temp element, and then finally what we store inside temp element equals whatever E-type we've stored inside temp2. So what that'll effectively do is swap 8 and 9. And if I swap 8 and 9, now notice the sequence is exactly what we want. The sequence we wanted abstractly is 2, 6, 9, 8, 7, 1. The sequence what we have in our implementation is 2, 6, 9, 8, 7, 1. So all of our conceptual pointer manipulations that would just say, well, start at the beginning and traverse down the list and print things out in order, that is how we're going to have to print out this list too. But now we've got the values in order. Yes, the node was inserted after 8 rather than before 8. But we don't care about the node. The node is an implementation issue. All we care about is that the implementation works, that it correctly supports the abstract view that we have in our minds, the mental picture. And this does. We've inserted the node afterwards, but the values were then swapped. So effectively, the value ended up before 8, even though originally it was inserted after 8. And in fact, the node that 9 is now in is not the node 9 started out being in. Who cares? It's an irrelevant issue because the user, the client of your class, never sees it. The client simply says, now that I've done this insert, if I traverse from front to back, I should print things out in this order. And that's exactly what will happen. So this is just a standard, 3-element swap, or 3-cell swap. And then here's the insert after code. Now you could condense this a little bit by writing current element directly into the node and save yourself that right. So there's a way you can maybe condense one line of code out of there in terms of the swap by remembering you're going to do a swap when you actually do the initialization. I'm not going to worry about that for the moment. But yeah, you could go ahead and say temp arrow element is what I pass into node, and then but there are better ways of dealing with this, and we'll talk about that in a moment. Or we won't actually. But I'll leave that for you to sort of figure out. Can you optimize one line of code away? At any rate, this will be constant time. It's the constant time that insert after was, and then a swap is just going to be constant time. So this insert before now is a constant time operation rather than a linear operation. So we thought all hope was lost, but it is not. We were able to insert before in constant time, rather than taking advantage of that sort of, a loop that goes from the beginning to wherever you are now. So that's insert before. Now the last interesting property to mention is that of remove, because we can do a similar thing with remove. So let me write out the list one last time. We have here head 2, 6, 8, 7, 1. And the conceptual view here is 2, 6, 8, 7, and 1. And we will have a bit of remove code. I'm not going to even write out all the remove code. Remove is just assuming we're deleting whatever is current. So 8 here is current. We're going to remove 8. And the question is, how do we do this? And once again, we might look at this list and say, well, it looks to me like the pointer that points to 8, 6's next field, has to point to 7. So if I'm going to get rid of 8, it would seem at first glance that I need to take 6's next field and point it around 8. Point it to the node containing 7, thereby cutting 8 out of the loop entirely, because now if I traverse from front to back, I go from 2 to 6 to 7 to 1. And ideally, yes, that's what we want. But again, we have this problem where we say we would have to delete 8 as well. We'll talk about that in a moment. But again, we say, well, I can't easily get to the next pointer of the node containing 6 in order to change it, because it's behind my current. And so as a result, what I could do instead is say, well, start at the beginning, traverse forward, the same thing we did for back 1, and the same thing we were going to do before insert before, or same thing we were going to do in insert before we found that better way. So all these situations where I need to access the pointer before my current node, they always suggest we need to start at the beginning and traverse a temp up to the node right before the current. And back when we had to do that, insert before, we managed to avoid it. Question is, can we avoid it for remove? And the answer is yes, in almost all cases. This case, certainly we can. And the secret to doing that is to remember that, once again, if I'm deleting what's current, All I care about then is that my element access sequence is 2671. I don't care about the implementation. So once again, if we can find a way of, in constant time, getting rid of the value 8, that focuses on the values rather than the implementation, that would be what we want. And we have such a situation here. Because even though I can't get to my previous node easily, I have this pointer here that 8 points to the node containing 7. I can get to the node containing 7 very easily. So why not do something like this, where I say current element equals current next element. That is, current element equals current next element. Or in other words, read 7 and write it into and over the value 8. And now you might see where we're going with this. Now that I've got step 7 stored over 8, 7 is stored twice, I can get rid of the first copy, which is easy to do because I have an address of this node. Therefore, I have this pointer. Therefore, I can point it around that node to there. So what I would have to do here is say, well, first, node pointer temp equals current arrow next. So I would point temp to there. Then I can say current next equals temp next, or I could say equals current next next. Either way is the same. But then that would take this pointer and point it to the node, a couple nodes down. And then finally, now that temp points to 7, I can delete temp. And that would eliminate this. And now I have 2, 6, 7, and then over here to 1, which is exactly the sequence I wanted. So we were able to remove, and again, if you look at this code carefully, all it is a couple pointer manipulations and a deletion. That's constant time. So I can remove in constant time, given a current location. If it's going to be a search and remove, of course, the search would take linear time. But if I'm removing, saying wherever you are, remove that node, that's a constant time operation, usually. So again, I'll give you a moment to pause and ask the question, when would this idea break down? When would insert, using just what we see here, when would remove not work in constant time? Under what positions, what state of the list or such would be one where the remove does not work in constant time? And I'll pause. And now coming back, the answer here is when we're trying to remove the last node. Because this little trick here depends on saying, I won't really remove me, because we don't care what node gets removed. All we care about is that the value sequence is correct. So we won't really remove me. We'll copy my next value into me and then delete the next node, which I can get to easily. So the element sequence is still maintained, and I deleted a different node than the one that originally held the value to be deleted. That works fine if we have a value after us to delete. But in a case where last node, 2, 6, 8, 7, 1. If I'm trying to remove the last node, I don't have that option. I have nothing after me I can copy. The pointer is null. So even if we were to draw it out like this and say, okay, this pointer points to a small null, there's still no value there to write in one's place. And so what would need to happen here, if I'm going to delete the node containing 1, 7's next pointer has to be pointed to null. And we say, well, that's a problem because I don't have access to 7's next pointer. I have to do the back 1 loop type thing, set a temp to here and traverse it all the way up to the node before current, which is 7, and then set that to null. So If I want to avoid that, I need to use the trick, which I can't use here because there are no nodes after 1. And so I am stuck here saying, if I have the last node, that would be order n to remove. Because I would need to do the back, looking at just that stuff there, I would need to do the back 1 algorithm. I would need to position a temp here, traverse forward to 7, and then say, for the node containing 7, its next field should point to null, or call delete on it and then point it to null. Now there are 2 ways out of this situation. The first way out of the situation is to have had a dummy node. Because if I have a dummy node, if 1 points to some garbage value that's just there to hold up a space for current to point to, so this is the empty set or whatever, this little symbol. In that case, I now have, for every single legitimate node in the list, I have a node after it. If I want to delete 1, I can write over 1 with some sort of whatever garbage data is sitting in here, and then say, delete this and point this to null. And I've deleted 1 now because now 7 points to null, which is exactly what 7 points to the dummy node, which points to null, which is what I want. So if I have a dummy node at the end, then I can always delete in constant time the current element because even the last legitimate piece of data has a dummy node. And we're never going to delete the dummy node, or we would hope we don't. That's part of the responsibility we have when we have a dummy node, is we don't position a pointer and then call delete. So what we would do here is copy the garbage memory of the dummy node into and over the value 1. And so we've basically done the same trick we did up here. So that's one way to solve this, to get constant time removal of the last node. Can use a dummy node at the end, or 2, what you could do is use what is known as a doubly linked list. What we see here is a singly linked list because the links work in one direction. There's one set of links. Every node has 1 pointer, so it's a singly linked list. What we will look at in the next lecture is a construct known as a doubly linked list, in which we will have 2 pointers for each node, 1 pointing forward, 1 pointing back. And if we have that kind of a situation, which we will explore in a little bit more detail in the next lecture, then removal from the end would be easy because you could always go back. The whole sticking point is gone at that point because going backwards is not difficult if you have a pointer going backwards. So you will see pictures of that next time. But those would be the 2 ways to get order 1 removal of the last node. You'd use a dummy node or a doubly linked list. If you're going to use a singly linked list with no dummy node, then you are constrained by the fact that the removal of the very last node is going to be linear time, and there's nothing you can do about it. Because your current points to the last node, and therefore can't get to the one before it. So what that means is, aside from that one last node issue, no matter how you're inserting into the singly linked list, it works in constant time. And aside from removing from the end, every removal works in constant time. And that's much different than the array, where all the inserts and removals were linear time, and here they're constant time. So in an ADT like a list, where we will be doing frequent inserts in various places, having things arranged as a linked list seems to be a good safe bet, because it means that your key operations, the insert and remove, are going to be constant time, where for the array they were linear. And so given that, we're willing to accept some time hit on things like back 1. We'll talk more about the time hits for various things tomorrow at the start of lecture, or next lecture at the start of lecture. But for now, that's about all there is to say about lists. Be familiar with the linked memory implementation, and of course be familiar with then the concept of how we would go about writing code for things like the insert and the, in this case, the remove algorithms. And so I will see you in lecture 10. Take care.